Мы продолжаем блок.
And we continue our workshop set. By the way, next workshop will be particularly interesting. If we need to create voice assistant, it has to be able to search at a good level. So our next representative is Nikolay Savushkin, in charge of SberDevices. He will be sharing the experience of creating a voice assistant from the ground up. But before, let me make an important announcement before I hand over the floor to Nikolay. Right after this workshop, at 10 minutes past 4 Moscow time, the representative of Intel will be hosting a workshop on software acceleration of AI. If you want to track and follow the algorithm alongside the speaker, this is important, listen to me. I need to create an environment and launch Jupyter server. It will take you 10 to 15 minutes, so start the Jupyter server in advance to follow the, not this section, but next session. Just be prepared. So, dear friends, 4:10 Moscow time after this workshop, the next workshop dedicated to software acceleration of AI. Please do bear that in mind. Be prepared. Start a Jupyter server. Now let's talk about how you can create voice assistant from the ground up. And let us hand over the screen to Nikolay Savushkin representing SberDevices. Hi there. My name is Kolya. I make search with SberDevices. My presentation is about making search fast without putting your head in your hands. So, let me tell you about how we created search for the Salute voice assistant family and what problems we have faced and what are our plans for the upcoming future. Salute is a family of voice assistants that are made by Sber. And you can use that voice assistant, for example, in a mobile app, or if you buy one of the smart devices that we make. For example, the TV set or smart display. You should be able to use Smart Assistant to search for goods at Sbermarket and Samokat, to search for films at Oko Theater, online theater streaming service, and of course there are SLA, and the requests are very different on voice assistant to compare to text queries. So that's why we need to make search with voice assistant in SberDevices from the ground up. A few words. We shall be speaking about what are the methods for information retrieval, what are the search engines that you can be using, and we'll talk a bit about how we have been solving the tasks at hand. Normally, we have Boolean model for information search and retrieval, vector space model, and probabilistic model. Today we'll be mostly talking about Boolean model and vector space models, because they're just practically more applicable. For Boolean model, it's assumed that we're looking for documents by Boolean queries. For example, you want to find the songs of Nirvana or David Bowie, so they will be finding the songs of Nirvana, songs of David Bowie. But you will not find David Gareth because there's no word Bowie. That is a reliable, time-proven method. It has been used almost in all of the search engines. It's quick, it's efficient, but it has certain quality disadvantages and disadvantages in terms of the scope of delivery. And we not only need to find the results, but also range them. That's why we'll be talking about the next step of Boolean model when we amend Boolean model with ranging model. A vector space model assumes that in some way you transfer the vector space, the query in the document, and then with the cosinus measure in the space of this document, you're looking for the nearest query. And we will be focusing a lot today on the first point. Why? Because in order to do search with SberDevices, we use the obsolete classical methods. Any AI Journey conference visitor knows that for information search and retrieval, it's better to use deep neural networks with transformers, etc. Well, first, the task of information search has been solved by humanity for thousands of years. There are some baselines of good quality. It's pretty easy to implement. They don't require a lot of resources. They don't need GPU resources. They have low requirements for tuning, and they allow to quickly get high quality. That's thing one. Thing two, inverted index. That's the data structure that allows us to actually implement Boolean search. As a key, you may store some sort of token, like a word, like Nirvana. And as a value, you can actually find all of the documents where you encounter this term. For example, all the songs of Nirvana. And for example, if you need to search for either Nirvana or David Bowie, you can look at all of the documents where there's Nirvana, all of the documents where there's David and Bowie, and find the important information over this range. So we can use neural networks that are more advanced. Why would we do all of that? So here are two options from Facebook and Taobao, where guys have integrated these approaches with vector models. But again, they have begun using these methods only in 2021, and you will see that Boolean search is not going away. And gradient boosting on the tabular in the trees is still the best option for tabular data. GBD is still SOTA in tabular data. We need to take into account context, popularity, seasons, time of day, surface where the search query is made. And here I would love to give a few examples from the guys in Yandex. They show that gradient boosting is still the best model. Let's now talk about pipeline. Normally, when people talk about search, they mean ranging. And in this triangle, they can be speaking about the top of the triangle, top of the iceberg. But search is not only ranging. Let us look at this particular image. At the bottom level, there's search index, all of the set of documents that we're looking at. That could be dozens or hundreds of millions if you're searching for items or songs. Then you need to make a data retrieval. So you need to make a preliminary selection, a subset from this index that could be returned as a result of the query. And only after that, you may start ranging after you have done the preliminary selection. You need to range documents. And you're not doing it using one algorithm, because mostly from the retrieval stage, you will get a ton of documents, because the mission of retrieval is to get the high recall. So all of the good documents would get into the retrieval part. If, however, you want your ML model to get the best results, you must tune the retrieval part as good as possible, so that it would be returning a lot of documents. You cannot get from simple Boolean or vector cosinus-based models get good quality of ranging. You can only expect that it will not lose the best results. So you get a lot of documents in return, like millions or dozens of millions. Still a lot of documents. You cannot probably range heavy ML models. So first, you will have to range it one more time, but now with use of a better mode, like a gradient boosting, but with a lesser number of trees or factors, or with a linear model. Then you'll be able to select out of these dozens or millions of documents, for example, dozens of thousands or hundreds of thousands, which is a good figure to range using your heavy ML models. Another thing that you need to understand when you make a system of search, it has to be distributed by all means. You cannot put all of the documents, which can be hundreds of millions, onto one shard, one machine. Even if you have good compression algorithms, probably you will not be able to effectively arrange that on one machine, on one shard. So you would need to build a search system that will be able to split apart, and every shard will be a particular independent search index, and you'll be able to process queries in a parallel way, and somewhere at the master or coordinator aggregate the result and deliver to the user only the top, the best that has been found on all of the shards. That's how you do horizontal scaling, by the way. Now let's talk about search engines that we have been considering when building our information search system. Obviously, this is not a complete list. It's actually a much broader list. But I have actually defined a few options here. OpenSearch or Elasticsearch. The project has recently split apart. One is done by Amazon, another is done by Elastic. We will be talking about them as a whole, because the search basis there is pretty much the same. There's Apache Solr and Sphinx. Those projects are less supported at that point. And of course, point 4 that you need to consider is creating your custom search engine. So, what are the advantages and disadvantages of these? If we speak about Elasticsearch or OpenSearch, it's a large community, constant updates. These are the products that are growing and getting better, getting new features. If something does not work out for you, you can even request a feature from developers. If something is not working out for you, developers may consider it. Or you can make, and they will add that feature after a feature request. Option 2, very important for us, is support for custom plugins, because as a matter of fact, probably as soon as you start doing your very own system, you will realize that you are lacking some functionality, because no matter how much the developer is trying to make a unified system, you'll probably have your very own specific requirements in terms of how you are going to conduct search. And probably you would like to add something to the code. And you probably don't need to make a fork for open source product, because then you will use access to the new features and bug fixes that the developers release. Plugin solves the problem partially. You can make changes to the code base of the project without changing core functionality and getting updates as you go along. Another important point is reach query DSL. Elastic is definitely reach in terms of query DSL. It's a large developed documentation. There are many ways, and amongst them you will probably find something that works for you. In the end, it has some disadvantages too. An important disadvantage of Elastic is that the system is written on Java. And even though developers are optimizing the productivity of the search engine, still Java naturally has certain limitations, and as the number of your documents grow, you'll have to be thinking about making your very own search engine. And I would like to specifically pay your attention to the thing that some believe that Elasticsearch is just a system for log storage. Yes, they do pay a lot of attention to that, and they develop this functionality. However, initially, Elasticsearch was created as a search engine per se, and it's based on Apache library that actually provides all of the search functionalities. So Elasticsearch naturally is a search engine, a fully fledged search engine. Don't see it as a log storage facility only. Now let's talk about retrieval part. We were talking about Boolean search and that it has certain disadvantages. That's true, because look, point 2, Metallica search query in Russian, Metallica, but we're looking for a band Metallica, written in English language. So a standard Boolean search doesn't stand a chance to find anything like that, because we have only Metallica in English. So even if we split the words into tokens like point 1, for example, We can work with morphology. Let us split lie not into words, but into some sequences of symbols, like 3 symbols, chargrams. Yeah, the difference will only be 1 symbol, and probably we'll find what we're looking for. But for the second point or third point, microwave oven as SVC in Russian language, again, that will not work. So we can broaden the query to broaden it for synonyms of your query. That's transliterations, acronyms, morphological differences. Word combinations, word modifications. Word derivation. Another thing that's very classical.
Ну и да, откуда вообще нам взять эти расширения запроса? Какие источники? Ну, понятно, что отличным источником являются... Да.
Or not to mention pet forms. So, where do we get query expansion sources? Well, answer 1, use all of the sources that you can get. Dictionaries. Any dictionaries, synonyms, word formation, word building, morphology analyzers. Your very own or open source works for you. Of course, World Wide Web, for example, Wikipedia. There's a ton of stuff on the web, like Wikipedia. Wikipedia is a great source for transliteration. You can find words written in Russian language or written in English language. It's pretty easy to deparse that and get a decent data set for transliteration. Of course, search logs is a great source for your sources expansion. If the person is looking for Metallica in Russian, the person is frustrated, erases that and does another voice query with the voice search. Next query could be Metallica in English or SVC in Russian versus microwave oven. You can see that in logs and actually improve the search. So understanding that what the person said in the first search is what we meant in the second search. You can use generative models. Another great thing. Transliteration is a task for machine translation, but not in terms of words, in terms of letters of acronyms. And any methods of machine interpretation and translation are doing that well. Any attention-based models and transformers are really applicable here. Gorgeous. You can do everything offline, so there's no problem with productivity. And you can also use similarity models, calculate similarity of queries, and therefore enrich the queries and expand them. Weighing, another important point, because it's not always that you want to use all of the synonyms to your query. Here's the example. B2, B2, that's the query for Russian band. Here are all of the possible options of what it can be made of. So, options from third till the last one, there's probably you don't want to deliver bees as in insects bees when the person is looking for Russian rock band B2. So you need to be able to use this both for retrieval and ranging. There are many ways to polish this up. Without going too much into detail, let me tell about the way that worked for us very well. We have been using the unsupervised model. We have taken all of our search bases, and we have actually trained a decent linguistic model, and we're weighing over this sort of queries with that model. So B-2 gets a low score because the band B2, B2 is never ever existing in this sort of writing. So we need to, no need to expand the query like that. That's why it has low weight. And the correct writing of the title of the band gets correct weight, better weight. So this n-gram language model was smoothing. help us to compare result. And you have actually below the link to the repository in GitHub with good implementation of this model on C++. If you're writing your services not on C++, there is a package with a library for Python, for example. Let's now talk about ranging. You can see here what we find if we're searching for Nirvana. We have the songs of Nirvana, the songs that have the word Nirvana in title. We have Nirvana Tribute, something else that contains the word Nirvana. So we need to range that somehow. Probably what's in the upper left corner, we want to have it lower. Be My Nirvana featuring Kind Rivers. Probably that's not what the person is looking for. So we can use gradient boosting tool. So also, what is our target? What are we using for training? As a matter of fact, we could dedicate another day to that. Let me briefly tell you that probably you will need assessors. That could be crowdsourcing, that could be assessor within your company. You can also mark up the relevance of the document according to the query, using some sort of scale, not just relevant, irrelevant, but from 0 to 3, for example. And also you need to dedicate a lot of attention to that. Markup is a key for good search. You need to invest a lot into how you're selecting assessors, how are you training the assessors, how are you correcting their orders. That's the whole other thing. But it's important to highlight here that this is assessor markup. When you're starting your search, probably you don't have any clicks yet, you don't have any stats yet. And of course, click-based stats is very noisy. What's on top, that's what's people clicking. So that's why assessors are a great source for ground truth. So since we're talking about gradient boosting trees, we need to select a good space of factors where you'll be using this gradient boosting tree. You need to improve it on an ongoing basis. Number 4, split documents by fields. You must do this, because often people love to put all the text into one large text field. That's not bad. If you have some way, even some heuristics, even manually for some popular documents, do that somehow. Split documents by fields, that will probably add better quality. Number 5, you see it's with the exclamation mark. It's very important. And it's not obvious at first. Active learning iterations. Active learning iterations. Let's talk about that. On the left, this is what your model may look like when you have trained it for the first time. You have just trained it using some sort of data set, and this is the result of your query if you say Nirvana. Nirvana Tribute. And some other songs. Why? Because the model has learned that there are many songs that correspond to Nirvana, and the model believes that this matches is good, but it's not only about matching, it's also about taking into account popularity. So the results on top are not that popular. However, model does not take that into account. We cannot ask assessors to mark all of the documents. It's millions and dozens of millions of documents. It's just impossible to do that sort of markup. So somehow we need to select documents that are marked by assessors, and they will be only marking those. How do we do that? Very easy. We will train the model to take a look at which documents are on top, and for those documents that we have not yet marked, ask assessors to mark them. They will be doing that while we're adding the data into our data set and retrain the model, and probably we'll get something like on the right. Still not perfect, but quite better than on the left. Iteration of active training is a key to good ranging model. You must take that into account by all means. Probably your first model will be bad or very bad. Now let's talk about features. Here's the formula. You don't need it. You don't need to read it with all of your attention. There's BM25 or BM25F. These are the factors, simple text factors, without the use of any neural networks. They will give you quite a strong baseline. There are 2 parameters, only 2 hyperparameters here. No need to tune up here a lot, but you can train those hyperparameters based on data if you really want to. These functions, these parameters differentiate functions very well. This is a very easy and accessible baseline that will help you to quickly get high quality. Now, let us talk about something less evident. We're calling it auxiliary keywords. Think about it. You're looking for milk, and you get the goat or cow milk, but cow milk is below goat milk. Why? Probably they're not looking for goat milk. If they were looking for goat milk, they would definitely highlight that. So there's the mismatch. What can we do this? What can we do here? We can use click data, a simple formula. In the real life, of course, it's much more complex, but let's look at the right side of the slide. For example, kartoshka. We have the word, we're looking for potato. And as a result, somehow we get on line 3, grid. Or net, or bag. Or people buy white potatoes or red potatoes. So that's why these are the results that we get. Color red, color blue, or boiling. So probably people do want the actual potato. Same we can do for bread. We can have bread, baton, baguette. In addition to matches, it goes without saying that ranging needs to be taken into account, not only matching. What else can we take into account? The query itself, for example, query token's number. How popular is the query? What's the class of the popularity? We can look at the document. How popular the document is, what's the file type of the document? We can take into account context features like season of the year, search from mobile or desktop. If you're asking your assessors to take into account the season, for example, your model will also be able to take that into account. For example, in winter you can show winter clothing, in summer, summer clothing. Now let's briefly take a look at the comparison of different ranking approaches. We have Nirvana on the left, and here are the results. And in every document, there is the relevance score by assessor, from 0 to 3. And we can train model as a regression. Just teach model to predict the score. It's called point-wise approach. Or we can take all of these pairs and actually write either 0 or 1 depending on the order in which they should be. For example, Smells Like Teen Spirit needs to be higher than Nirvana Yorsh, and this odd song Be My Nirvana should be lower than Nirvana and Nirvana Tribute. This is called pairwise approach. Pairwise approach. Everybody's saying, yeah, let's use pairwise approach. So good. Because it delivers better quality. That's true. Thanks to the expansion of the data set, you'll get better quality. But you need to understand this. When you move to pairwise approach, you're losing the coherence of your scores. Previously, your scores predicted the relevance score, so you could cut off the threshold. If you have pairwise approach, you can compute all the scores by 2, and the lost model will not change because of that. So the model can compute all of the scores by 2 or 10, and your threshold will stop working. So if you want to be able to cut off irrelevant elements like Lord of the Rings and not show the film called Lord of Love, although both results have the word Lord. So one of the results, you can use pairwise in the re-ranging, and of course, even more features. What can you do after that? You can add factors that are specific for your domain, like using vector spaces to do retrieval of documents, not only Boolean search. You can add neural networks as factors, as text matching for your rich factor space, and also use clicks as a teaching target. You can teach separate models for those clicks, for user activity, and use models like these models like factors, or combine them with your models so that you'd be able to take into account not only relevance from assessors, but also make your search more personalized. Therefore, I conclude and thank you. You can use this QR code to learn more about our research and our articles. The presentation is also available. Thank you. That was really awesome. A ton of useful information. Listen, there's a range of questions that our audience is asking you, Nikolay. Let's answer them quickly because that was truly engaging. Question number 1. What's the difference between your voice assistant and other voice assistants? For example, recently we've launched a neural network called RuDali within the Salute voice assistant. You can tell it a phrase, launch RuDali and ask, draw me kittens, and wait for it to draw you a Dali-styled kitten. Awesome! Cool! Students from California University in Berkeley have found a way to launch voice assistant Siri, Alexa, Google Assistant without the knowledge of the owner. Does your voice assistant has algorithm to block that sort of violation? The question of security is more about the team that does IT security than the search team. You should understand that. But in SberDevices, we're very serious about security. That's why I strongly believe that we have been trying to defend against that as well. Another question, what sort of devices in the future would replace Smart Assistant? What sort of devices, in your opinion, replace Smart Assistants? Look, probably what sort of devices can replace smart devices, because Smart Assistant can be launched within the mobile app, and then it cannot replace any other device. It will only be a convenient function in your app on your smartphone. But if we're speaking about what sort of devices can replacing with smart devices, I'd say that we can improve older devices, like you have an old TV, and it's not smart, and you buy SberBox, you install it into HDMI, and your TV becomes a smart TV. When you were saying about a ton of voice assistants, I recalled when my kids were ordering film and Knocker saying, add some chips to us too. And there's a QR code on screen to pay for that. For me, I mean, as a daddy. When you were teaching ranging models, were you doing relevant and non-relevant markup with pairwise loss? That seems to be easier as opposed to group-wise approach that you were mentioning. It's interesting what sort of experiments you tried there. We have been trying binary markup, relevant, irrelevant, and markup with more grades of relevance. We actually decided 4-point grade is better because it covers different aspects. Of course, we tried different approaches. We tried point-wise, pairwise, list-wise approaches as well, and list-wise approach works well. But in my slide about point-wise, you can see why pairwise is also important. Final question. How do you verify your models of ranging in production? That's a good question. As a matter of fact, it's clear that quality assurance is a range of metrics. When you're doing search, in the end, you want to improve your product metrics and your online metrics. That's why you need to track those which we're doing. Maudao retention and this sort of search metrics. However, we cannot only look at them. That's why you need offline metrics. That's why, by all means, at the assessor evaluation, we have offline metrics that we're measuring. We have even dashboards, and we're regularly looking at the quality of our models. Sweet, Nikolay, thank you. It was a pleasure. Dear friends, we continue.